Alright, this is the introduction for the calorimetry lab, and this is all about the conservation of energy. Now, when it comes to this lab, please go ahead and answer this question ahead of time, and you can answer this question ahead of time as well, but don't forget to answer them because for some reason, this one in particular, people always seem to miss. Now, what we are going to do is we're going to mix some hot water and some cold water. I don't have a equipment list printed out on this particular lab, but let me show you what you need. You need the hot plate. These are shoulder height all around the room. You need this research grade calorimeter, also known as a styrofoam cup. You need a beaker, and you need yourself a graduated cylinder. Where are you going to find these guys? Well, if you look in the direct back of the room, in the dead center, you're going to see the beakers right here, and you're going to see the graduated cylinders right here. Send someone tall. When it comes to measuring the water, pretty much always use the graduated cylinder to measure the water because you get a much more accurate measurement than using these beakers. You can use the beakers for heating water up and for transferring liquids. You need this temperature probe that's going to measure the temperature of the water as we mess around with it. You're going to need this metal sample towards the end of the lab, and you're going to need these pair of tongs, which I always seem to forget to get out to handle the hot beaker. Now what we're essentially going to do is we're going to mix some hot water and some cold water and actually have a nice little simulation that's going to show you what we're going to do. You're going to get yourself some water, and you're actually going to get yourself 50 grams of water. One thing to note is 50 grams of water is 50 milliliters of water, which is 50 cubic centimeters of water. This is going to be roughly 20 degrees Celsius, or room temperature. If it's not exactly 20, don't entirely worry about it. And then what we're going to do is you're going to get yourself some more water, and first we're going to start with equal mass, and we're going to start with unequal temperature. So you're going to use your hot plate to heat 50 grams of water up to 60 degrees Celsius. We can go ahead and heat these guys up, and this thing is actually really cool. It shows you the graph view and macroscopic view, and you're going to dump the water into the calorimeter. This is essentially the styrofoam cup. Doesn't have a fancy stir thing. But one thing to note is that we have the hot water that's all wiggly and jiggly like, and we have the cool water that starts off not really wiggling and jiggling so much. But at the end of the day, they kind of meet in the middle. Because we started with 20 degrees and 60 degrees, it's probably, gives you a warm fuzzy feeling that it finishes off at 40 degrees. That's more or less what you're going to do in the lab. Now, the difference between the lab and this is a simulation and this is perfect. And in the real world, we're going to lose some heat to the environment. You are going to stir the mixture as this occurs because, well, the quicker this the quicker this process happens, the less heat is lost to the environment. One word of caution that I have with this particular lab is if your faucet looks like this, if it doesn't have a little aerator on the end, then the water is going to come screaming out of these pipes. Open the water very, very, very slowly. It will spray you. It will spray your partners. It will knock glassware out of your hands. So that is my public service announcement for this particular lab. Let's pop back to the Word document. So what you're going to do is first measure the mass of the calorimeter. This is essentially going to allow you to tare it. You're going to put in 50 milliliters of water, and you're going to go ahead and measure the mass of it just to prove that everything works. You're going to subtract the two, get the mass of the cold water, and you're going to measure the temperature using the temperature sensor. Don't worry if it's not exactly 20. Then you're going to heat up about 50 grams of water to 60 degrees Celsius. If you overshoot it, that's okay. Don't entirely kill yourself. Give it a few stirs with the temperature probe and go ahead and dump that into the calorimeter. Immediately stir it and keep on stirring until the temperature kind of equalizes. Don't allow too much time to go by because, well, the more time goes by, the more heat's lost to the environment. You're going to measure the mass again, subtract the previous one from this, and you get the mass of the hot water. Then what we're going to do is we're going to calculate the temperature change of the hot, temperature change of the cold, and then what we're going to do is we're going to calculate the heat lost by the warm and the heat gained by. In order to do this, what you're going to do is you're going to say, I know that Q is equal to MC delta T, and you're going to do this for both the hot water and for the cold water. Then all I want you to do is to say, wow, gee whiz, look at that. The heat gained by the cold water looks a whole awful lot like the heat lost by the hot. It's not going to be exact. There's going to be more heat lost by the hot than gained by the cold. But that's kind of what you expect, isn't it? Then what we're going to do is we're going to use this to predict the temperature if we mix 100 grams of 60 degrees Celsius with 50 degrees of 20 degrees Celsius. And what I want you to do is I want you to say essentially that the heat that is lost by the warm water, so that would be the heat that is lost by the warm water, is equal to the heat that is gained by the cold water. Because it's gained, I'm going to put a plus sign right there. What I'm going to have you do is I'm going to have you solve for what the final temperature of the system is using the mass of the hot, the mass of the cold, the temperature initial of the hot, and the temperature initial of the cold. I don't want you to necessarily put values in just quite yet. You're going to do that on the next step. So now you're going to go ahead and substitute the masses and the temperatures. Now all I have you do is test this guy experimentally, and does it agree? If it doesn't agree, then something really bad happened. The very last thing you're going to do is you're going to get yourself some water, and you're going to get it, and you're going to put that into the calorimeter cup, about 20 degrees Celsius. Then what you're going to do is you're going to get some hot water boiling on the hot plate. Actually, if I were you, I would go ahead and get the hot water boiling on the hot plate while I did this step just right here. Then what you're going to do is you're going to record the mass of that metal sample. That's the piece of aluminum that I showed you, and you're going to lower that guy by the string into the boiling water. It will immediately stop boiling, and once it starts boiling again, you're going to know what the temperature is. The temperature is going to be that of boiling water, probably 100 degrees Celsius. So kind of expect that guy right there. You're going to take the metal out of the boiling water, and you're going to put it into the calorimeter with the 20 degrees Celsius water. You're going to give that a couple of stirs with the temperature probe, wait for it to equalize, and you're going to measure the final temperature. You're going to say how much heat was gained by the cool water, and that's going to be using essentially the MC delta T that we're already all familiar with. So what we're going to do is we're going to say the heat from the water is going to be the mass of the water, specific heat of water, change in temperature of the water. The heat that was lost by the metal must have been the heat that was gained by the water. So the number right here should be the number right there, only negative. Then what you're going to do is you're going to say, I know what the heat of the metal must be. That must be the mass of the metal, the specific heat of the metal, and we're treating that as an unknown. And this is going to be the change in temperature of the metal. And you're going to solve this guy for the specific heat of the metal. I'm kind of telling you that the metal is aluminum, so go ahead and calculate your percent error.